So for the benefit of the recording today, what we're going to do is we're going to cover the ASTM standards. We're going to look at Dogbone testing. And what I wanted to do first though is literally look at this. Now I set this up just because it's just an easy bit of thing, and this is a really old example that I was given quite a while ago, to be honest. And it's a bit of a pain in the backside. There's a few things there where you kind of go, damn it, there's a midpoint there. So with that midpoint, now I realised, as somebody said to me, they went, there's no actually real marking to say that that's in the middle. It's like, yeah, that's a really good point. So if you got annoyed with that, that is my problem. Apologies for that. That's absolutely true. I should have really put a marking on to say that that was in the middle. But it was in the middle. So if you did put it in the middle, thank you. But yeah. So the reason I put it on there is it just gets you a little bit more comfortable with navigating yourself around. I should point out this week is probably going to be the last week that we're going to center a lot on verification, and we're just going to move on a little bit because I do really want to start looking at assemblies, and I want to start looking at a little bit more in depth of composite materials. Just because if we spend too much time on verification, we're going to lose even more stuff that you're going to learn. So it's a trade-off sometimes, it really is, because we could spend the entire module just looking at verification all the way through. Right, so with this was a Ford seatbelt clip. Those of you who are old enough, because I know there's a couple of you, you'll remember these types of original clips. They came in Ford Capris, they were in all sorts, and they were a very simple plate. Since then there's been a lot of modification on these clips, but this is a very old style of clip. Now it was an example that ANSYS set up a while ago, and originally they set it up to be done in a system called APDL, which is the DOS version of ANSYS. We could use that, but I really don't want to waste your time, just because I think that a lot of you guys are industry already, and I want you to have more skills that make you more employable or more attractive towards bigger roles within your workplace. So that's why I'm focusing more on the workbench approach. If anybody is interested in APDL, please do let me know. I do have notes to support it, but it is such a pain in the backside with many things. So like, for example, if you make a mistake, there's no undo. If you make a mistake, you're just going to start again, and it can be something that took you 10-15 hours to develop. It's very temperamental, let's call it. Right, when it comes to this, you didn't need to have the center line here. All I'm going to simply do is take my overall length, put it over 2, and then put this over 2 to just give me where that point will sit in space. Again, I should have really pointed out that that was a distance across it, and that it was symmetrical in understanding, but yeah, I didn't put that on, so apologies guys. Right, I don't want to waste a lot of time with this. Well, not waste a lot of time, I don't want to spend a lot of time doing this, but I do want to work my way through it. If you haven't done already, please can you open ANSYS? You see, what I'm going to do is, to make sure your licenses are all free, is I'm going to run my old copy that I have from the desktop here. So you'll notice I'm on 19, but you guys will be on 19.1. It means anything I generate here, you'll always be able to open. Before we begin, has everybody been able to access ANSYS? If there isn't, do please put a point in the chat. Because I am trying to feed this back to LIS. They've found some interesting things with the system. It literally can only filter levels of people accessing, trying to open the license at one particular time. If it gets an influx, it's kind of like a non-Newtonian fluid. It just locks up. So it's like having 1,000 people trying to get through one doorway in one go. It just jams solid. And it's a really odd way, but hey, I don't make the software, so I can't whinge too much about them. So again, I'm recording this. If I do go a little bit quick on this, apologies. It's just I wanted to quickly show you a few things about this simple seatbelt clip. So as ever, I'm going to drag and drop my static structural. And with this, we do need to bring in a different material, but first things first, I'm just going to bring in my new design modeler. If you are Space Claim savvy, please do use Space Claim. There's nothing wrong with Space Claim at all. It's just I'm just more used to using Design Modeler. Anybody who knows Graham Calderbank, you'll know he says it's a very similar thing as well. There's nothing wrong with it. It's just I'm just more used to using Design Modeler for producing things like this. Right, let me just bring that on. So, as ever, I'm going to choose my plane. So I'm going XY. Then I'm going to go Sketch. A few ways of doing this. I mean, I always say CAD savvy, and I know it sounds a really odd thing to say, so I'm going to look at first. But it's just for those of you who do have a lot of experience doing it, because I know there's a few of you in this group who are very experienced at doing it. You'll know that the painful process of what this actually is. So what I'm going to do is just draw a rectangle, snap it to the origin. Again, just as a reminder, guys, when you snap to an axis, you'll see a rectangular box snap to the origin. You'll see it go square. I don't like using square, but so I'm going to bring that out. And when I've done any CAD system, when I've done any CAD drawings before, I've always preferred. 2 seconds. Is that actually on the axis? No, it looks to be on the axis. I've always preferred to draw my pocket. So I'd always draw the outside window first. It's always been a thing for me. So from there, I'm going to go dimension. Now with dimensions, as ever, I do like to be able to see the value. It's just because I'm particular like that. So I'm going to go general dimension. I'm going to come to my horizontal, then come to my vertical. And we know with my vertical, oh, see there I'm in meters. There's no units on the drawing. That's awkward. It should have been millimeters, which I think a lot of you already knew, but I'm going to go units, change that to millimeters. There we go. So on my horizontal, I'll go 38.1 for my horizontal. For my vertical, I'm going to go 38.02. If anybody's wondering where these odd values came from, by the way, it all came because the original drawing was done in inches. It was that old, it was done in inches. And I thought, it's a nice example, let's just keep it. But then you look and go, Also as well, I'm just, oh my god, I'm missing loads of stuff here. Look at that. I haven't even put the rad on that edge. In fact, I think somebody did ask me about it. They did. So the rad on this edge. So I'm going to go radius on. Oh, that's been awkward. Why is that not giving me a radius there? I'm not going to waste too much time with this. Let me go draw. I tell you why, it wasn't letting me pick it. So I'm just going to go modify list. I'm going to go fillet. And on my fillet here, this fillet now is 6 point. Oh, hang on. Let me just bring that back before I lose it. I'm going to make this fillet 6.35. 6.35. I know I can imagine there's a few of you who are already on CAD now and just going, well, I've done it already. I know, don't. I know. And then from here, what I'll do is put on another rectangle. So I'm going to go draw, another rectangle. I'm going to bring my rectangle in here. First things first, let's just get in the dimensions that you were lucky enough for me to add. Oh, you swine. Try that again. There. No. Okay. Cancel. Right. This is what annoys me with this system sometimes as well. You've got to put it in like that. So all I've done there is pick out my top upper edge and then to my vertical edge here. Really frustrating sometimes. But anyway, again, we don't make the system, we just use it. 1905. And we have a width between the two, which is 9.53. And you start to see now it's starting to say take form. Right now, I can never work these things out in my head. So what I'm going to do is go 38.02 minus the 20.72 and then divide that by 2. 8.65. So this distance to here, 8.65. That's all I was after then. Whoops. And that is 8.65. And we have a size of that of 20.72. Again, apologies if I'm going really quick on that one, because I appreciate a lot will be following, but this is not really the notes I was going to go through, but I just wanted to go through it because there were some really good questions coming out of this, and I didn't realise that I actually applied this on Teams just because, for this reason, because often when people are set bits of challenges, you come away and go, does it tell us this? And that's what I didn't know. I wasn't sure what people were thinking, and it kind of helps me, if you will. So there, like that. And these, let me just show you where they came from, just so you know I'm not having you on. 1.59, 0.79, and we've got a thickness of 2.5 millimeters. And all we're going to do now is just run this through the mill, so to speak. That's my drawing. Happy with the drawing. Going to go to model, and I'm going to go to extrude. We know that that thickness is actually 2.5 millimeters. And I'm going to apply it to the sketch, and then if I've not balls that up, because it froze a bit then, click generate. And if you've got it, that's the type of thing you should be getting. And that's the seatbelt. I'll upload this afterwards. It's just for anybody who was getting annoyed. When it came to that centre line, for those of you it left you a bit not sure whether it should be on there or not, apologies. I put it on there thinking it might explain a lot for you, but in fact it actually confused a few things because you were missing key things, like for example the middle of the line, and that apologies, you weren't really told that that there was symmetrical, and I just went through the assumption, so apologies for that. Right, so that's our geometry set up. I'm going to close that. Always feels strange that, because you know it's like with the system, you're always waiting to update it or change it. So we're using an aluminium 3003H18. Now the one thing I didn't think about is I wasn't sure if it was in this system. So what we'll do is we'll pick a material. I don't want to spend lots of time on it, that's all. I just want to take you through this initial process and the important thing about it. So I'm going to go to edit my area. On here I already know that my generic straightforward material is structural steel. If it comes in and it doesn't look like what I'm looking at here, by the way, if I go to view, see I've got reset windows and layouts. That will allow you to reset things. It's just in case, because I've had some people who said to me when I opened it up, I didn't see what you did. So do go to View and Reset Layout and Workspace, and it'll just reset to ANSYS standard, just so you guys know, because it can be a little bit frustrating, a little bit annoying. So right, go to my engineering tool, data sheets. Again, if it's not here, apologies guys, I should have really checked that if it was in here. Under my general materials, so we have an aluminium alloy. It's not under classification. Yeah, it's really not here. I didn't think to check here. For this, I'll use an aluminium alloy because I think it should be to the power of 6 for its Young's modulus. So go on to here. Power of 10. This alloy is a lot stronger than the 3003. Now, just for if anybody wants to know, let's say you wanted to upgrade this aluminium alloy and you wanted to make your own version, which is not uncommon. A lot of people do want to do it. What I can do is from here I can actually copy this. I can copy the data, and if I wanted to, I can actually start to edit this and make a new version. So if you have a particular alloy, so if you're from automotive, if you're from aerospace, anything like that, you can edit your data sheet, your data here, or if you wish, you can always go to actually build your own model up entirely. I'd never really recommend that. I always hack and slash materials first that are on that same realm, if you will, that same area of what it could be the topic may be. Just to show you though where you would pull a data sheet like that. I do need to find this out because we did have a system, we did have something on the system called Cambridge Material Selector. Phenomenal for what we do. You can just pull the data, import it to ANSYS, done. But I don't see, I can't seem to find where it's gone. So what I do, what I've always had as my go-to is a website called MatWeb. And MatWeb is an online materials information resource. It doesn't look very sophisticated at all, but in fact this is phenomenally good. So if I just type in, this is just for your information. Don't worry about going off and building materials. It's just in case you want to know one. So if I go 3003-H18, I'm sure a lot of you already use it. I've got here is the actual grade of that. What I'll do, Jake, is I'll try and freeze up a little bit, and let's see if we can just get everything running back in speed again. The good thing is the recording that I'm running is not recording through the bandwidth. So if there is losses there, the recording will be consistent. And that's one of the reasons why I record to the hard drive, so that if something does go wrong, it's not something for you to worry about. There is a way for you to always catch that back up if there is an issue. So this is 303, and this is the classification for it. Excellent, excellent. So yeah, this is the classification for it. So we've got the ultimate bearing strength, our bearing yield strength. We've got all the key aspects and modulus of elasticity. You can actually see here it's actually not the strongest stuff in the world, and its behavior actually should be to the power of 6. So it's gigapascals, and it's giga or mega. I always get the two mixed up, but anyway. This material is fairly weak, and interestingly, when we ran this through the other system yesterday and it actually was just inside of that remit, but there was no real indications to say why it had or why it hadn't. Now all this data, if you're ever going to come to rebuild your own data, all you actually do is you come back in, and basically it literally is this. So you look for your density, you go back to the side, and you just gradually build it that way. Or if you are very brave, you can actually build the material from scratch and just make a blank material. I'd always just rip them off, which sounds really dodgy to say that, but it just makes life a bit easier for getting around, and it just gets a bit annoying otherwise, because if you look here, you can get export the system. Now if I go to export the data, you go, oh, that's where they start to make the money, and they really do make their money because they can export to all of these. And this has become quite a popular thing to it. This is rivaling Cambridge Material Selector, and it is a phenomenal resource. So unless you've got lots of money, because I mean, let's have a look how much it cost. Oh, hang on, that's just premium. Oh, I'll come back. I'm going on a massive side note there. I'm going to have a look at that. I just realised that they may have introduced a free. I like free. They may have introduced a free option. Right, so back to the point. I'm on aluminium alloy. I'm just going to use the aluminium alloy because, again, my big thing with this is I just wanted to run it through and wanted you guys to look and go, well, did it pass? So if we go to aluminium alloy and we look at the Young's modulus. Now don't forget, Young's modulus is a ratio of stress over strain. And it's a test result from that stress over strain. So we know that. And with further analysis on this, if we take something like ultimate yield or ultimate strength, so ultimate strength to the 3 to the power of 1 e to the power of 8, 10 to the 8, yeah, you actually look. Basically, it's strong, but when it goes, it just fails, this alloy. Because you look at the strength, it goes, but when you get to this ultimate area, it actually lowers in its strength. And it's just because there's barely much elasticity to really support around it, which is interesting. Anyway, so let's move back. All I'm going to do is close that and go into my sim and then edit. So don't forget, now I've actually got 2 separate materials that I can choose from in this simulation. Oh, apologies. Yawning like mad. Right, here we go. You'll notice as well, I did put a red herring in the question. I don't know if anybody spotted it. I'm just interested to know if anybody did spot it. Right, so I didn't move to verify this. I was doing a bit of verification with a bit of a fag packet calc, and I can get roughly in that area. Really need to break this down even more, but all I was interested in is would it be safe under this level of loading. So we go to the solid, we know everything's set, everything's good. I'm going to go to update my mesh. Now my mesh might come in a bit more clumsier than yours because this is the older version. It's not too using a space navigator, and they are very sensitive. Now it's a bit clumsy, a little bit chunky. For me, I'm just going to make that a little bit more finer. I can tell you from the start that wouldn't really satisfy me. I'd need just a bit more refinement around these particular areas. So that's all I've done. I've just gone to my relevant tolerance center and just tightened it up a little bit, that's all. Then from there, I've gone to supports, fix support, spin that round, click onto the back plate, and apply. So this is just presuming it is fixed. And then I'm going to apply my 96.53 megapascals on the face. So I'm going to go force, apply there, I'm going to use vector because it is pushing on that point. So the value I'm looking to apply is 96.54 megapascals, but this is in newtons. What value should I be entering? Again, this is in. I tell you what, I've never tried. Let me just try first, because I'll be gutted if this works. They keep making it easier and easier. 5.3, and I'm just going to see if it'll let me put in MPa. Nice. So what value should I be putting in? Because megapascals 1. So let me go. And yes, I'm just should I not be putting in pressure? And yes, I should be putting in pressure. Now, what I was actually alluding towards is that don't forget that the unit change between megapascals and Newton millimeter squared are comparative. They are equal to 1 on each other, so they will jump backwards and forwards. This is a pressure that we're applying onto it, because don't forget, again, for those of you who are old enough, when these things would lock solid, they would really lock solid, and it would be completely down this point. I actually do think, if I remember rightly, these are still used on commercial airliners. I think this particular design. So with this now, if I just go 96.53, and then we'll just go MPa. Okay, 96.530. 96.530, would that be mega? Because it's 3, isn't it? I was thinking, because mega's 3 onto the Pascal, I think. So 96, 1, 2, 3. Okay, so now hit run. So I'm going to solve that. And again, I'm just interested in here whether it will surpass what the material will support. One thing that I've totally forgotten to do then, I've just realized, is under my solid data here, I'm still set to structural steel. Should have been on aluminium alloy. So I went to solid under assignment and changed it to aluminium alloy. That is my fault. I forgot to change it. So I'm just going to resolve that again. And what I'm looking for now is to see if the output surpasses the Young's modulus. So if I go to, I'll just go to equivalent von Mises just to give me the output in megapascals of what it'll actually do. And if I evaluate that, (7e to the power of 5), it's still a factor of 10 out of its ultimate tensile strength. It has suffered quite a big hit, but it's not enough for it to fail. In other words, this material would probably survive. This material would probably be a good option if you were going to use this as that level of support, but it would also rely on whatever the people were after. So if they're after a particular level of factor of safety, you simply take out your maximum stress and divide it out by your ultimate. Is it 6? Oh, sorry. Yeah, I keep getting all them bloody things mixed up. So, I always think it's 3. Apologies, yeah. Yeah, so I'm yeah, this might practically explode. 96.53. That's better, yeah. So it's 9653000000. Yeah, this might come back a little bit more damaged. So based on that, we're down to the 8. 738. So coming back onto my unsaved bit of work here. Just come onto my data. I just want to look at the aluminium alloy. The Young's modulus confirms that it's to the 10. The ultimate tensile strength is onto the 8. The bulk modulus and the shear modulus is still at 10. So this will have suffered some level of deformation. It will have bent slightly, but it will not have failed completely, because the Young's modulus and the bulk modulus, the shear modulus, is still holding in place. So it will have saved someone's life. That's what's the most important thing, because obviously the 80s, especially now, all it is really is these seatbelt clips are just there to be tested as to once. You can pull, and I should have really pulled. It'd be nice to. I'll speak to my friend from ASTM and see if I can get the actual standard for seatbelt clips, and then we can upload that and perhaps revisit that, or I might even introduce it as an assignment. But it's a great example. It is a great example, and it was just a bit of fun, just for people to get used to using this. And I hope for those of you who had a go at it, you did find it useful, just to navigate yourself around and getting used to using it. If you don't want to see the mesh, which really, if I wanted to start looking at verification, I'd need to start tidying up that mesh. Not the best mesh in the world, but it's a good indicator of the type of values that I'll be seeing. So just to answer, will it survive or will it not? And the truth is it will survive, but it probably would need replacing. That will be my first initial thought on this. But again, to get better value, we'd have to run it through greater detail. Right. Quickly, I'm going to save that because just so people can refer to it as what I just set up, you can take a look at it yourself. I'm just going to stick on my desktop. And I'll just call it seatbelt. Okay, so that's a seatbelt, and I can start a new project now. So I'll just go new, and I'm into a new project. Right, so the actual set of notes that I wanted to work through. These are ones that I tried to put together. Now, there's probably going to be typos, things like that. If I do make a typo as I'm going through, please will you just drop me a line and let me know that you spotted a typo or something like that. This drawing is not to perfect scale, but it just gives you an idea of the drawing that we're going to actually create. These values came straight from the ASTM standard, and you'll notice, I'm just going to quickly call this ASTM standard up. This is the old version, and it's just because a friend of mine, he wasn't sure whether I was able to use the up-to-date version, because obviously you've got to buy the up-to-date version. So this is your tensile testing for materials. You've got very, very specific standards about how this is set up. Very, very particular processes for what you're actually going to be doing for calculating tensile strength. Now, all we're going to be doing is verifying stress, strain, deformation. That's the 3 things that we'll be verifying with that. We can move further and further down the line. Now, these values here, I've actually taken these, and I don't know if I put it on the notes. Oh, I should have really put that on there. That'd be better. And I have built these together. Now, the important thing with a standard is to always keep in mind that you're operating to a gauge length. This is the idea of that. It's this area that you're looking at failure points for, because this and this is for your fixture points. And you'll notice here this is actually a section. This isn't a revolve. Now there is a sectional piece here. Now this is the one that we're actually going to be building, and we're going to build based on that, based on these values. And I have plucked the values that we're using from these standard sets. So if you're looking where I was making these values up from, it was from here. I put it on here just for your entertainment, just for you to take a look through. They were very specific. Now, Sean Bird from the company Tinia Solson, he'd suggested that we run tests to 20 kilonewtons. And so that's what I said. I said, right, we'll run a longitudinal loading to 20 kilonewtons. And then based on that, all I've done then is try to calculate out the tensile or compressive stress due to normal loading, which I've just realized that doesn't really make sense. Compressive stress due to normal stress should be normal loading. And as I said, there will be errors here and there. And then I've tried to calculate out what my strain deformation will be, just to give me a ballpark figure to actually operate around. And then at the end, I've tried to calculate out what my overall change in length will be due to the stress. On here, just so you know, when I upload these notes, you'll find all the notes and how to actually build this up manually. But I'm going to do this anyway, and I do want to move relatively slowly with this, and I just want to make sure that we can cover, because beauty is there is a resolution issue, let's call it. But I want to show you if we can explain these problems, that's fine. So what I'll do first is I'm going to bring in my static structural. Again, anybody who's CAD savvy, please do, you can model it on your CAD system if you want, and you can import it. So if anybody wants to import from this geometry, right click, go to import geometry, and make sure you output your CAD model as a step file. Output it as a step. That's going to be your best one, or you can use an IGES file, one of the two, but I'd always recommend step. But for me, I'm going to use New Design Modeler. When it loads. Okay. So let me just show you the values I'm operating to, which is these. So that's what I'm operating to, and I'm simply just going to start drawing this up. 2 seconds. Apologies, it's just freezing up on me a second. That's my own, that's not that one. Right, there we are. Right, so what I'm going to do is come to my XY plane. I always use XY. It doesn't have to be that if you don't want it to be. So I'm going to go stretch. I'm going to go sketch. Right click and then go look at. Brings in that XY plane, and all I normally do is just draw this. There's two ways you could do it. You could either do it as two rectangles if you're a bit more advanced in this. You could do it as anything really. It just depends which way you want to go with it. But what I'm going to do is do it in lines. So I'll do line. I'm going to do a center axis line, a horizontal line here. Then I'm just going to draw another point up here, which will be vertical. Draw another line across, which is horizontal. Draw another line vertically down. Come on, you swine, where are you? Then another line across. Whoa, I just realized if you look there, it's not connected. Do that again. Draw another line across, horizontal. Draw another line up, vertical. Draw another line across to that end point here as horizontal, and then draw a connection between them two to close off my geometry. Doesn't look very sexy, I know. It's not very well put together, I know. But we're gonna get this well sorted now. Oh, sorry, stiff shoulder. Right, so I'm going to start bringing in my dimensions. I do actually think these notes, by the way, I actually think are on Blackboard now. You can. This sounds dodgy, but you can get them now. But you can get them now if you do want to download these for yourself straight away. I will be double checking today anyway, just to make sure they're there. So all I'm going to do is start dimensioning. General, there, and then there's my first one. I know my first one is going to be, just double check, I'm sure it was 20mm radius. It is, so obviously this, because we're going to revolve this is 10. Oh, that's meters. So I'm going to drop my meters to millimeters. So I'm going to go 10. Damn it. Okay. I've got to operate like this just to bring it back down a little bit. So this is actually 35. I'm making a real fudge of this one. I'm going to go down to my central axis, because I do know with my overall length of this is not 2 meters. My actual overall, well, I mean just under 2 meters, is 162. And at the minute it's a lot bigger than 162, so I'll go 162 millimeters. This is going to make it a little bit more drastically smaller. And then from here, so it is 10 millimeters across. I just want to know what that is. 7.5. It's 3.5, isn't it? That's 12.5. No, 6.5. Sorry. Okay, so I'm going to bring that in as well. Wow, that's really gone horribly wrong. So I'll go for because that's my actual middle line. I've made a real fudge of this, by the way. Just cancel that. Bring that general back in again, and I'm just going to come from that point. Take it to there. No, I'm just thinking because it's really not worked out well, that one. Okay, I'm going to have to move that. So let me move you. Oh, I made a real fudge of this one. Right. 2 days in a row I've had this disaster with this bloody drawing. Okay, 2 seconds. I'm going to just fix it. I'm going to make this length, because this length by 10, so it's 10 millimeter out. So it's yeah, it is. It's 3.5. This length here should be 3.5. So 3.5. And then, bloody hell. Let's see what we got at midpoint. My goodness. So I'm going to make this. This, again, is actually 35. There we go, and it's starting to look a little bit more like it was meant to look from the blooming start, really. And see if it'll let me just move that across. You gonna let me move you across? No, because that'd be far too simple for you. Let me just put in a constraint. If I'd have done this a little bit more differently, it would have been a bit better. So let's have a look. That's why. So my dimension here is my horizontal dimension there is not making my life a bit easier, really. So I've got my distance there, and I'm just gonna rebuild that because that's just gone horribly wrong for me. So I'm gonna bring that into there. I know that that is going to be 10 millimeters. So I've just deleted them lines just to make my life a bit easier because it's been a pain in the backside. Come on to line, and then there, and then bring myself a line to there. Like that, and I'm just going to have to trim these two. So I'm going to modify, and I'm going to go trim you and you. Wow, what a disaster that turned out to be. Didn't need to be neither. Right, and this again is 3.5, or what I can do is put the actual dimension on there, which was 6.5, I think it was. So come back, 6.5. Dimension on there, and we go here and here. Okay, I'll go this point and this point. 6.4. Now it's red because I just over-defined it. And the last thing I think this needs on here is that all important 35 millimeters attached. So we're going to 35 millimeters attached on here. And now that should be your overall drawing. Got there in the end. Happy days. Should have 35 millimeters. It will be vertical across, so that will be related to here. So everything should be fine now. What I need to do is revolve this. So I'm going to revolve this profile, obviously 365 degrees, using this central axis here to give me that shape of the dummy itself. Or the sample itself. I'm now going to go for a revolve. I'm going to choose this as my geometry, and then it wants the axes, like any CAD system, it wants to know where that axis is going to be. So click axes, click apply, and then because ANSYS is very backwards like this, if I click generate, then the all important geometry will appear. Just minimize that, and let me see if I can just hide that out. So I'll hide the sketch, and then 2 minutes. Apologies. Right, so now I can just navigate myself around a little bit, and that's my first level of drawing. One thing that frustrated me with this particular system is applying this fillet. So if you look on here, it's not really a fillet. I mean, everybody knows a typical fillet to be acting equally between two perpendicular lines. And it will equally balance itself out between two perpendicular lines. Now what I'm going to actually do is create a blend. And applying these fillets like this is often better if you just put them into the drawing. One thing I found on this is I was struggling to actually find the best way to do it. If anybody does come across a better way of actually applying this particular profile to it on ANSYS, not on CAD, because I know you can do it on CAD, but I was interested on here, the best way of doing it. So if anybody does come across it and spots a better way, please do let me know, because I've been playing with this and looking at it thinking, what is a better way of doing this? Now, on here we've got all these little different features that are on here. So we have obviously our concept. This is where we could create new profiles, different aspects. We've got create. Now with create, we've got fixed radius bend. We've got various radius blend. Sorry. And we've got your skin to loft. There's some really good things that it'll do. It is still, for me, very much primitive in many ways. But there's some really good stuff that it can do. So what I'm going to do is a fixed radius blend. And what I want to do is, apologies, I've just, so we've got blend there. So if I go fixed radius, my radius in this case is going to be 27.5. Just so you know, 27.5 radius. And then from the geometry, whereabouts within this geometry are we going to go for it? I'm going to go, well, I'll show you what happens. We'll go on the inside edging and then click OK, click apply, and then generate. And you look and go, well, 27.5. Update. That's what we're after. But you see there, because I've been clicking on there, I forgot to hit, that was me just there, I forgot to hit control. So I'm going to do that again anyway because I just messed that one up. I'm going to go back to create. I like to go the long way around just so you can see where things are. I'm a fixed radius blend, and I'm going to press control because you'll see here I'm at 27.5. I'm going to press control on the inner section for where the let's call it gauge to grip point sits, and gauge to grip point sits. I press control, don't forget, on both because that's what I just did, that was wrong. So click apply and then generate, and that is our first sample piece, or as they refer to it in the States, our specimen. Again, I based all these on particular from the ASTM standards, and something, those of you with me yesterday, you're not allowed to answer this question, but there was something that I came across and it was so strange why it was happening, not sure why it was happening, and I'm just curious as to who may notice this. So that was me generating the parts based on there. And if I come back to the theory that I'm working to, you'll see here I'm working to my longitudinal loading by pi r squared, which is 6.5 obviously because that's the rad of the center gauge area. And then I go by my sigma, and my sigma by Young's modulus, which in this case is structural steel. Again, I've just gone with the standard. And then that gives me my strain deformation, and then from there, pi r squared, yeah, and then from there I've gone to displacement. You notice on my displacement I've gone with my sigma by G. In G in this case, did I put G down? I'm starting to think I didn't. No, I didn't. I should have actually put on, at least I've noticed that before you guys saw it. G is the gauge length. Now my gauge length that I was heading for was 50 millimeters. So this area, 50 millimeters on the inside, and that's what that is based on, and that's what the displacement should be. Should be in that ballpark figure. And if I come back and now move on, so just playing around with this in particular area for the standard, we're going to now close that. So I've now got that set up. If you've not done already, I would always say get this saved. So I'm just going to go on my desktop and I'm going to call this Dogbone. ASTM Dogbone. ASTM Dogbone. So put this on here. It is a very standard set of standards. There's actually about 50 of them, different variations for different conditions, different types of materials. There's all different ones out there. If anybody is interested in particular ones, do let me know, because I actually know the guy who's writing a lot of these. Come on to model, and I'm going to edit. I can go into setup and go edit. It takes me to that same spot. Again, I'm using structural steel. And there we are. Typical standard set. It's exactly as I imagine. It's brought in the actual data set. It's brought in everything that I need to see. And there is my sample, my specimen. In the geometry, just to check, brought in my solid structural steel, sorry, as normal. It's brought in everything that I need to know, the coordinate space. It's told me where that's going to be. Now you'll notice here I don't have a tab called materials, and it's just because 19.1 added that in, and I don't have that there. So if you do have that there, that's good. That's just because you're using an updated version rather than me. And your meshing, you probably won't have to mess as much as I will in this, but we'll see how it goes. So moving forwards, now what I want to do is, I never know for sure what mesh is going to be best, never know for sure what's going to be the best way forward. So all I'm going to do is right click and go generate mesh as the first initial step. I mean, instantly. The good news is it's the type of mesh I would expect, because don't forget, if this thing's been put into tension, it's been pulled apart, it means that this area is going to be moving axially down that x-axis. And if it's moving axially, we know that the best type of mesh for this is not going to be triangular systems. It's going to be more of quadrilateral methods. So your 4-point brick approach, or as one student said to me once, the way that this looks, it looks like the old style brick entrance to a shit house, which still stuck in my mind for years. So this type of quadrilateral approach is far better, and well, for this it is anyway. So what I'm going to do is, the only thing I'm not convinced with is this looks very light in refinement. So I'm just going to drop this down a little bit, just make it more to a medium refinement, and then update again. I do personally think it's a good start as an application. I do think that is a good start as an application. Some of you guys may have found that your mesh may even look even cleaner than what mine does. It just depends. But I think, again, I do think that is a great start. So I'm going to come into my my loading. I'm going to go into static structural. I'm going to right click, go to insert, and I'm going to go to fixed support. And obviously now I'm going to fix this area, and this is going to be fixed in its place, where in essence I'm just going to pull this thing apart. Click apply, and then I'm going to go back, right click, I'm going to go insert. Now this, in this case now, is a force. We know that it's a force, and it's going to move down that all important x axis, and I'm going to apply components in my x axis. As ever, it is not, sorry, I just had something come through on my watch. It is not negative, because we're moving with that all-important x-axis. We're going into that positive axis. So, and as I said at the start, let me just come back. I do like to keep referring back to these notes, because at least then you know I'm working from something rather than just making stuff up and leaving stuff incredibly confused. Oh, I did point out where it is. Thank God. 20,000. So in that much respect, I'm going to go 2, 0, 1, 2, 2. 20,000 newtons active in that X component. And then I'm going to... Oh no, I'm in. That's it. Yeah, I was just looking there. I've got everything there. Just to confirm, it will give me a little bit of an arrow, which is just there, just to tell me its overall direction in which way it's moving. Or you can see down here from the tabular data that that's telling me how it's going to move. We can do an incremented approach. I don't know who's really interested with this, but I go 0.5 and then go 10, 1, 2, 3. What it will actually do is it will iterate that process, go through them processes, and then build up from there. So if I go to here, for example, it's iffy when it comes at 0. It doesn't like to be at 0. It needs to be at a particular value. So if I go 500, I can do that, and that will allow me to iteratively apply the force, just because you never move an object. These machines, anybody who's run these tests before, you'll know that these machines move at a key level of speed, and you get a variation of force being applied gradually, and then you move to failure. It's just something for you guys to take a look at if you want to see it. What I'll do with this is just keep it at that minimal for the moment. If anybody was with me yesterday with the nightmare that turned into COMSOL, I've uploaded the video today where I've done that in COMSOL as well. I do want to revisit that a little bit more, where we're going to have gradual force being introduced. But for this, I just want to run it through and let's see what type of result that we get. Right. We are getting to that point now. It's going to start looking a little bit iffy if I don't start to save. It's just because these systems, they're great, but when they fail, you lose everything. So always make sure you have a process of just resaving and resaving. And I know you get this automatic recovery and all this, but sometimes, you know, when you go, that is not what I saved, or I might have saved this like 10 hours ago. Do keep that in mind, is that you can't rely on the automatic recovery, because it can really stab you in the back. I've witnessed to it myself many times, where you just want to scream and throw something at the wall, and it tends to be your laptop. So let's run that through. I'm going to go solve. If any of you guys are interested in me getting Sean from ASTM, Tinius Olsen, to come in and just give us 5 minutes about what he does in his role as a materials testing guy, please do let me know. I will more than happy to invite him, because this guy will talk your ear off about composites, about testing of materials, and about really the types of things that he gets involved with. Because as a background, he was formerly, he'll kill me if I get this wrong, but he probably will kill me anyway. He was formerly American Special Forces Diving Division, I think he was, years and years ago. But he's incredibly experienced. So if anybody is interested in me bringing him in as just a bit of an extra, just for you to listen to some of the stuff that he's done, then please do let me know. So for the solution, I'm going to go insert. I go this way as well, just because everybody doesn't realise that doing it this way, if you hit your, because I've had a lot of people before who've run the solution and gone, oh hell, I didn't put the stress on. They've hit run again, and sometimes if it's something like this, it's 2 minutes to run. If it's a big simulation, you could be talking days, and it's nice to know that you don't have to run it again. You can just use the present solution to extract the all-important values. So first things first, I'm going to go stress, and you do look and go, what? So you got your equivalent von Misers, you got your intensity, you got your shear. So if I come back and you go, right, okay, then that's tensile stress, tensile and compressile stress. I put this into brackets just because, in case anybody didn't know, it's known as normal stress. You do look and go, okay, yeah, normal stress. This is known as normal stress, and it's just the way of resultant of the normal stress with it. So if I click on normal, and you instantly see there that it's talking about axial loading. So we've got orientation of that normal stress. We were using a longitudinal load. We're moving that force down that axis, and we're saying, look, just give us that, because that's where we're calculating from. And then what we were then looking at is then what we've been looking at is strain deformation. Now, under my strain deformation, it always plops out. It actually comes out in maximum principal strain for elasticity. That's what I'm really looking at. So yeah, maximum principal elasticity strain. Apologies, guys. Sometimes I actually move between multiple softwares, and I can often get myself mixed up which one I was actually looking at. Hence why I keep backgrounds on it. So I'm going to add in my maximum. In fact, it's not been solved yet, so it won't give me anything. And finally, based on the equations, I was looking at changing length due to stress. So I'm going to right click, insert deformation, and I'm going to go total. Do we go directional? Because really I'm moving on the x-axis. Let's go total, and then for argument's sake, let's go directional and just look at the two between them. And obviously my direction is still in the x-axis. I think we're going to be happy with the directional, because that's what we're really looking at. We're looking at that the displacement around the x, even though it's a three-dimensional geometry. And then all I do is evaluate all results. Coming to normal stress, so let's take a look. I'm just going to turn my mesh off for the minute, like that. And as you'd imagine, if I just run that through, yes, it extends out. It concentrates around this area. We know that this point's going to be a failure. We know that that's really what the type of value is that we're looking at. So 159, 151. So 159, 151. So there is, I mean, that's my thing at the minute. Is you look, it's actually saying between 1.4 to 1.5, that value should be recovered, and it does give me a lot of strength and confidence that I'm actually in a good position to do that. I can now start to go back a little bit, and well, once I start making my way through. So let's take a look at strain. Strain is 0.7. Well, it's 0.000, but let's take a look at what we get. So if I go principal strain, 0.007. Come back again. 7.3, 7.8. So there is a little bit of inconsistency. I'm sure you can all appreciate that. Again, though, it's within my operational boundary, so I'm still confident with what I'm getting. It's giving me a lot of confidence, saying, okay, that's good, I can operate with that. However, if I get to total deformation, 7.2 directional, total directional. I'm going to actually just delete that. I was just being a bit pedantic, really. I'm going to just stay with directional, because obviously it's all coming from X. If I was going to go total, it would be about something that was far more geometrically complicated in comparison. So just run that again. As ever, it goes through the process, but we're at 7.2. So come back again, come to here. We're at 3.7. But these are tying in. No word of a lie, this did stump me. And I know some of you are probably sitting there going, well, it's obvious. Any thoughts? And it really is this simple. If anybody's sitting there going, surely you thought that, I didn't. I really didn't. I looked and thought, well, I don't understand it. Okay. It's really silly. Don't forget, we've got a gauge length. So the gauge length is larger than between these two. So we have this gauge length. So the average is going to be pushed higher, right? So we know the average looks at the same value of what we should be getting, but it's going to be skewed. So in other words, it's taking fixture points here and here in, and that's being added into that displacement. If you actually measure the gauge itself, we're still accurate and we're still looking in a very good position of 3.7. Now, I've not actually written into the notes to actually isolate that by using probes. In the end, my biggest proof with this is that if you look at the average actually is very close to where we need it to be. I'm going to add some more to these notes to actually segregate that down by using probes. But I know this is a real cop-out, but I didn't get time to do it because at first I was looking thinking, why is my strain right? Why is my stress right? And why is that given? And I just didn't think. It's because of the actual fixture points here and here. Now, the other thing that I did allude to is I made a mistake. And, oh, have we got a question? Do. Okay, so on your strain, right, yeah, good point. I've had a question, well, not a question through, I've had a statement through that a strain is coming through for some people at 0.008, and I'm at 0.0078. And yes, it could be that mesh. What we're going to try and do now is refine a bit of mesh, and that process is going to be on it. Now, this has come about because of the 19.1 change. Can I just ask, said person, can I just ask, you've got a limit. So I'm at 0.78 and I'm at 0.69. What is your range between, what range are you getting between there? So I'm imagining your 0.008 is your upper range and you'll have a lower range. I'm just curious, is it still in that ballpark figure? Right, yeah. Yeah, so yeah. Comment back was that the upper and the lower range is looking at 0.008 and a 0.0071. So arguably it's still within our all-important 7.5. So it's still within the operational value, but still this mesh, it's the mesh that's doing it. So when I really hope these discussions, because I do like these to be discussions, so please do come back and go, I found a better way of doing it, because I'm dead keen to hear it. But I really do like these discussions just because you should be starting to see, if you get somebody who waltzes up and says, yeah, I can do FEA and hits default, you kind of go, wow. How do you know? How do you know that there's something there that's realistic? So if they're just looking at the deformation of the material, if they're applying a force onto a key defined material, which has been well defined by Young's modulus and testing, then they're building on present knowledge. But you need to know that. But if you're talking about this type of thing, how do you know that you're looking at something sensible? And this is the only way to really introduce these discussions and debates, let's say. Right, so what I'll do then is I'm going to push back to first. There's so much in this. It's absolutely crazy. I'm just trying to think about what's the best way to move forwards. Okay, now the other thing that I can't really show on here very well because I can't find the best measuring tool on here. Now, what I was hoping for is that this area would give me a good solid 50mm gauge area to operate with. It turns out it actually cuts the tip off completely. The resolution of this bend at 27.5 is actually just slightly higher than what it should be. So what you end up with is something more along the line of 49.6, I think it is, millimeters of gauge area. And I went back through this and I sat here for days going, why is it not matching exactly? And where this error was coming from was actually coming from that fillet itself. When we've been, because we're actually moving now to doing 3D printed materials, looking at this type of thing, and it's got that frustrating that what we've actually done is we've used these systems to generate what we're actually going to make. We've then extracted these key values for verification calculations, and then we've printed exactly what our systems are making so that we're getting an exact thing to operate against, or else this might turn into something quite embarrassing really, because you'll get there, always have this error, and you just won't know where it's coming from. So this actually came from the resolution on there. So part of this inconsistency on this result is actually coming from that slight change that's on there. You kind of sit back and go, ooh, that's a shame. Right. So the other thing is now let's try and tidy some of this mesh up. So I've come onto a mesh, and that's what I got. And I mean, arguably, it is a good mesh. It's not so bad. What I would like to do is add a few extra things on it though. Now some of my meshes on here, you'll have even better options on yours. So I'm just going to go insert. Now on here there's a few things I can do. I just wanted to play around with a couple of options here. So if you look here, I've got sizing. Sizing's pretty good. So when sizing comes in, what sizing says is, okay, so what do you want to size and how big do you want it to be? So let's say this area here is not really my main point of interest. This area is where all the action's happening. So I'm going to click apply on that face. Now this is cool. You see how here I've got default mesh. I can say I can actually choose how big each mesh piece is going to be. Now don't follow me on this one just because it's going to go. I'll show you the level of nodes this thing can make. Now this is meters. So let's just see what it'll do. So let's have a look. Oh, that's actually not so bad. But you can see there, it's divided it down that even more, just to give me that little bit more of consistency right across the board. Arguably, as a friend of mine said recently, what you should really consider is incorporating these in as well. But if I go, I mean, you can go crazy with this. I had one student one year who went, I've gone 10 to the minus 12 and it won't mesh. And you look and go, wow, it's not had time to mesh. And it was just a black dot. So you look there, now if I zoom this in, zoom in, you can see there it's divided these areas down even more, right down. Now what it actually does is it will mesh this down, and what it will try and do is have a ratio that plays across. So you see here, even this has now been shrunken down as well. What I'll do is bring this back to something sensible. Just have a look and see how that looks. Oh, I mean, I've actually made that bigger. No, that's not good. So we bring that down. Just to give me some good operational values within there, and that's the type of thing. So you can see that's been refined in that particular area. And the other thing is you can see here on these ends that it's, I suppose on these points here, it doesn't need a lot of refinement because that's not really my major focus point. But what I'll do to make sure everything is happy, I'm going to insert and I'm going to apply a method. Now these methods, I love these methods, and I can't remember if we did one last week, but these methods are phenomenal. What these methods will do is they will apply what will be the best. So I'm going to apply onto there and click apply. And what it will do is it will do the face sizing based on its automatic, and then it will select through all the different procedures and try to amalgamate all of them together. Now this can either work out really well or really poor. So if I update that and just take a look, then come back to my mesh, and you come back and go, not really done much, is it? So I'm going to say I actually want a multi-zone. Now, for anybody who's not sure, anybody who's used to ANSYS, you'll have seen this before, multi-zones. So we talked about quadrilateral, we talked about tetrahedral, and there is multiple variants within that as well. If I use what's called a multi-zone, it will try and take hexagonal, quadrilateral, and a parametric type approaching to try and create me the most efficient type of mesh. Now this is monstrous. It is really good what it will do, but it can slow down your PC drastically. We will be introducing this when we do a bullet. We will need to. The bullet moves so quick, it needs to be able to refine itself quickly as it's moving. So you look there, it's gone through the process, it's looked at different areas, what is the best way forward. Now I like looking at these ends, which sounds odd, but I like looking at these ends. You can see there we've got combinations of rectangular structures through to quadrilateral structures. I don't even think, amazingly, I don't even think I can see any triangular structures there. They all look to be mainly quadrilateral deforms. So like there, for example, they're all quadrilateral deforms, which that is the type of mesh which would be for me the very first move forwards to making something a bit more approachable. Now again, to show you what I did under my face, so I'm just going to suppress this. I'd like to show you through this process again, just because I know I can race through and get too excited with all this. So under my face, sorry I keep pausing, it's just I do have questions that roll in. I just like to make sure I'm not missing anybody out. So what I did is I went to my mesh, I right clicked, I went to insert, and then sizing. Sizing's always been there, it's a great tool. When I went on to sizing, what I wanted to do is to make sure that my gauge area was taken into consideration. So when gauge area came in, I was in a position where I had to choose somewhere. So I just chose that, which is my central point. Then applied on there. And then I've right clicked again. Now I've done this again just because I love multi-zone. Sounds really nerdy. So I've gone to insert, and then I went to method. Again, I'm just slowly repeating this just because I want you guys to know what I'm doing, why I'm actually doing it. These are just little tools that have been placed in the mesh to make our life as engineers much easier than having to go through the painful process of physically setting up a mesh piece by piece, which some softwares still do offer. And in my multi-zone, I'm just going to reset that back so you can see exactly how it looks. So reset that back, and let me just go multi-zone, and that's how originally it comes in. So when it comes into multi-zone, all I did is I selected on the geometry, because I'm just saying all my geometry, if you find anything that is of poor standard, please update it to give me a more relevant result. And I hope you guys are really starting to see as well, it's all in the mesh. Next week, when we do move them to assemblies and we start to look at assemblies, we're even going to see the magic happen, where if ANSYS brings in an assembly and tells you something's right, you run it and you go, no, that is wrong. And that's what we're going to be looking at. Really, in many ways, what I'm trying to do is actually show you the limitations rather than ANSYS saves the day, because it just won't. So I'm going to go insert, and then on my method went down. I can use sweep, but multi-zone, because I'm happy with what's above, my multi-zone just means that it will look at different areas and try and refine based on the best computational ways of solving it. Again, it is an axial output, a longitudinal output for the loading that we're putting onto it, but I just like to be sure that that's there. And this for me is the very first best, well, this is the best move forwards for me. It's a good move, it's well refined, and what I'm going to do is, just because I know that I'm getting to a dodgy spot now, I'm just going to hit save. Anything that I'm doing, by the way, guys, I will be uploading it, so please don't worry if you've got along, it's died, ANSYS has not worked, something's gone wrong, please don't worry. I'm going to be uploading it anyway, for at least for you to digest and look at it and kind of go, oh, this worked for me, it didn't work for that. So I'm going to hit solve, and now we wait. So, normal stress, 1.6 to 1.4. So let's go back to my loading. 1.15. I mean, I'm still in there, but it's offering now that even slightly higher. Now, some could argue that by doing that, what I've done is made it too sensitive, where you've got nodes passing over the top of each other. Perhaps my multi-zone is a little bit too much of a heavier going with it. The trouble is the result it was giving wasn't too far out anyway. It was actually very close. Let's just go on to the principle. So now this is interesting, really interesting. Maximum principle elastic strain. The look on this, we're actually operating now to 0.7 to 0.79. So if I look back on now, I'm 7.5. So technically I'm closer. Just out of curiosity, said person who messaged me with the result that you were getting for strain, how does yours look now? Does it look similar to mine? Are you getting the same type of result of 7, 9 and 7? I'm just curious as to the solver, because I do know that 19 and 19.1 they updated the solvers, so I'm just interested if you're getting a better result than me. Really? That's really odd. So you're actually now get no. It's not at all. It's you've got, you see now, just to pan back, you're not doing anything wrong. Just to point out, for anybody, I'm just realizing I'm reading out these points here and I'm having a discussion where nobody else is not clear what's going on. So just to point out, the point that he got before was he was getting 0.008. This was 80024. Now this one, the new result is suggesting 008027. Now you've got an increase. Now just to point out, I've also got an increase as well. But your solver is actually giving just a slight deviational change, as mine's much more drastic. So you can see that there's a lot more accuracy coming out of your solver than mine, because it's able to concentrate these values better. But I am really confident. I mean, you look at these results now, we're well within that right ballpark figure. So for me, so I'm in 7.2 as a displacement. My average is 3.3. So I will figure out a nice way to isolate that area. Actually, I need to do that. So if I just jump back, my actual value was 3.7, and this is 3.3. So I'm very, very close in that right value. If I isolate that down, that will give me a much more accurate result of what my displacement on that extension of a bar is. So I'm confident there as well. But the beauty is now I would be nicely, comfortably in a position where I could easily start to perhaps generate this component and move to a test. So I'll work when somebody sends me a picture that's on its side. Yeah, I can see where you've been going with that. Your dependent range there, but you're looking at that displacement that you're getting on your extension. This was only just because I've taken from the gauge. That's all it was. But you're right. That verification there does pull it out even greater as to where that's coming from. But yeah, the only reason I'd done that is because I was shipping straight from the ASTM standards, so I was taking straight from there. That's all that was. But yes, you're absolutely right. Okay, so just to answer to that, it's a good way. It's a definite good way for verification past there. Absolutely, absolutely. Now the only reason I stayed with the gauge is the machines that we've been using from Tinius Olsen, they will actually only take into consideration the gauge, and but yes, that does give it that. My point is yes, you are right. Yes, you are right. Right. So this was just a bit of an intro as to using the type of standards and the reason for using these types of standards and setting up ANSYS to allow us to do something like that. We'd now be in a position where we could start to move to varying different things. If you wanted, if you knew what the speed of the thing was moving at, and you wanted to look at that force in a force curve being introduced, all you need to do is just add that in and start to vary that change across it, and it will give you that gradual change in there as well to actually give you a far more accurate representation of the force distribution. Because at the moment, obviously, this is just a resultant that comes straight out, and that's what we're operating to. Right, so I'll upload these notes. I'll double check that I've uploaded these notes. All the stuff that we've done is actually sitting in here, just to show you that everything's sitting there. And again, if anybody's interested in more of these ASTM notes, the ASTM standards, please do let me know. I do have an awful lot of these just because I'm on the panel. If anybody does have any more ideas with this, or if anybody has any questions about this, please do get in touch. What I'm thinking about doing is going through a standard example, but doing it for composites, and that's where I was going to ask Sean to see if Sean will come in and give us just a 5 minutes example of the types of stuff he does with Tinius Olsen. But the composite standards, these composites are in Dogbone shape. So those of you who've tested these before, you probably have tested these before. They aren't in the cylindrical format, they're in a thickness format. So the same profile, but they're a thickness to them. And yeah, right, so let me just save that. Before I draw a close on this, is there any burning questions on what we've really done with that? Right, so what I'm going to do is stop my recording.